All right. So in the last class, we did application of integrals. We covered areas under curves. Okay. Today, we will do volumes and surface area of solids of revolution. So as you can see here, that's our topic for today. Volumes and surface areas of solids of revolution. Now, look at the first one. So volumes of solids of revolution. So let's say there's a curve. X, Y, and this curve is y equal to f of x. And it moves, and we are considering this curve, this segment from x equal to a to x equal to b. Now let us say the first case, volume of solid generated by revolution of the area bounded by the curve y equal to f of x, the x-axis and the ordinates x equal to a, x equal to b. So this is the one. Now this x equal to a and x equal to b. Now this is the shaded area. Now this area is revolved. This shaded area is revolved about the x-axis like this whole revolution. So what happens if we do that? It forms a whole volume so it forms a whole volume like this, and this is just we are seeing from this way, but it is completely a circular volume. So how do you find the volume? To find the volume, so when we are revolving about the x-axis, so to find the volume, now let us take a strip. This is dx. So this distance x, at this distance x, there is a small infinitesimal differential strip that we have taken. The function value here is f of x. So now when we revolve this about this strip about the x-axis, so we get, all right, I'll draw in red, we will get a circle. We'll get a circle of radius f of x, or radius, I should say, y, of radius y, and it's a circular ring. In fact, it will have its own thickness. So it will have its own thickness, and the thickness is equal to dx. Anyway, it's difficult to, it's a ring. So it's a flat circular plate kind of a thing. Okay, thickness is dx and radius is y. Okay, you will get like this. Now, once this is, so you get a disk. You get a disk of this. All such disks. So this disk I'll extend here. So this will be the disk. Now all such disks from x equal to a to x equal to b. That's what we have to integrate. So what will be the volume of this disk? dv. dv. Volume of this disk will be pi r square dx. So this gives the volume of this disk, and all summation of all such disks from x equal to a to x equal to b. Therefore, the volume will be integral pi r square dx from x equal to a to x equal to b. So what is our r here? R is nothing but y. So pi y square dx and pi y square dx integrated from a to b. So that's what we get. So this is what we have when we revolve about the x-axis. Suppose the curve is revolved about the y-axis. Very similar thing we get. Let's draw that. So this is the curve. Y is equal to f of x, or we can write x is equal to g of y. They are the same curve. All right. Now, what we do, we want to find the volume of revolution of this curve about the y-axis. So it revolves about the y-axis. Now this is y equal to a to y equal to b. So now this time, if we have to revolve about the y-axis, we have to take the strip like this. This is dy and this is y. This length is y. So at y, this point is x comma y on the curve. So here, this is x is equal to g of y. We should write like that. Now we revolve this thin strip about the y-axis and then we get a disk again. Now this time, so this length is x. So the radius here will be x. So in this case, dv will be pi x square dy. Pi x square dy. So volume will be integral pi x square dy from y is equal to a to y equal to b. So that will be the volume of the solid of revolution. So with respect to when it is revolved about the y-axis, we have to integrate with respect to y. When it is revolved about the x-axis, we have to integrate with respect to x. And now suppose sometimes the curve is given in terms of parameter. Now volume of solid of revolution of the curves between the parametric points t1 and t2 about the x-axis and about the y-axis. So if it is about the x-axis here, so we have pi y square dx integral a to b. This parametrically can be written as pi y in terms of t. You have to substitute that, and dx will write as dx by dt times dt. Convert the limits from t equal to t1 to t2. That is what it is. Pi y square dx by dt into dt integrated from t1 to t2. Next, similarly, if it is with respect to if we are going to revolve about the y-axis and integrate parametrically, we'll get this parametric integration. So about the y-axis, you will get pi x square dy integral y equal to a to b. This will be same as pi, substitute x in terms of t, and dy, y is a function of t, it's a parametric equation. So dy by dt times t dt from t1 to t2. So x we'll write as f of t and y is g of t. So y dy by dt is g dash t. So this is how we do integration with parametric form of the equation of the curve. What if the equation of the curve is given in polar form? The equation in polar form. r equal to f of theta. So now we know what is relationship between polar coordinate and the Cartesian coordinate. It is very important how the revolution is taking place. So here the revolution is taking place about the initial line. So initial line is like revolution about the x-axis. And we know that x is equal to r cos theta and y is equal to r sin theta. Relationship between Cartesian coordinates and polar coordinates. So what do we do here? We replace, so integral will be integral a to b pi y square dx. Y will be replaced by r sin theta square, and uh, x will be replaced by r cos theta. Now this is d into r cos theta. Now it depends on how we are integrating. So we'll get if we are integrating with respect to theta, which mostly we do, so we replace d times r cos theta by differentiate it with respect to theta multiplied by d theta. Okay, so dx is dx by d theta times d theta, like that. Similarly, if the volume of solid generated by revolution of the curve about line perpendicular to the initial line between the points theta 1 and theta 2, then what do we get? Okay, we get this pi x square dy integrated between a to b, and we get this pi r cos theta square dr sin theta by d theta d theta. So y I am replacing by r sin theta. So this is about volumes of solids of revolution. So when we do problems, it will be clear. Now surface area. Surface area of solids of revolution. Okay. Surface area is simple. The same volume. Let us go to this. We are talking about the surface area. So we don't talk about the internal volume, only the surface. So the surface area of this disk will be the circumference times the thickness. Okay, this is not this surface area inside. It is talking only of this rim, thin rim. Okay, and when it gets revolved, it revolves like this. So we are talking about this surface area, this shaded portion. With this surface area of revolution will be the circumference 2 pi y times dx. Now, truly speaking, this is not dx. The surface area we will take as ds here. This surface area is ds because it's a curved surface area. It is not a straight surface area. So therefore, we get this one, 2 pi y times ds. 2 pi y times ds. Just a second. Sorry for the distraction. So now, so surface area of the solid generated by revolution is this. So area bounded by the curve y equal to f of x-axis and the ordinates. So about the x-axis. So you will get 2 pi y ds, circumference times the thickness of the curved surface area here. This is y, so 2 pi y into the thickness. Now ds we know from the rectification length. Now we have to integrate with respect to x. So we have to convert the ds in terms of x. So under root of 1 plus dy by dx whole square times dx. Now if we have to do it about the y-axis, let's go and look at here. I want to get the surface area here. So this curved surface area here will be ds. And what is this portion ds? And this is x. So 2 pi x, we are revolving about the y-axis. So 2 pi x will be the circumference times the curved thickness ds. So 2 pi x ds. Now ds we have to integrate with respect to y, this one. So we write ds as under root of 1 plus dx by dy the whole square dy. Remember, for both of this, ds square is equal to dx square plus dy square. Okay. So ds by dx will be divide by dx whole square, and dy dividing by dy whole square, you will get this. So that's how we can find ds. Now suppose we have to integrate with respect to find the surface area parametrically. So then we have to do this generation solid of revolution with respect to t. So you can do now about the x-axis means 2 pi y ds, about the y-axis means 2 pi x ds. Once you write this, once we write this, after that y is substituted in terms of t, then ds will be substituted as under root of dx by dt whole square plus dy by dt whole square times dt. That's what we do. And finally, surface area of the solid generated by revolution of the curve r equal to f theta about the initial line. So this is in polar form. So about the initial line, so it will again be 2 pi y ds, y is r sine theta, and ds, remember what we had done, ds square is r square plus, sorry, is dr square plus r d theta square. So based on that, ds by d theta we want. So divide by d theta the whole square, you will get r square plus dr by d theta whole square. Under root, you will get ds. So that's how we do it. Okay, let's do some problems now on this topic. So last time we did areas bounded. Now let us do the volumes. First, a very simple problem. Find the volume and the surface area of the solid generated by revolution of the circle or revolution of the curve, x square plus y square equal to a square about the x-axis. About the x-axis. So we know when you, so x-axis is a diameter, and if we rotate a circle about its diameter, the solid of revolution that is generated is a sphere of radius a. So we know from mensuration what is the volume of a sphere, 4 by 3 pi r cube. So r is a here, so 4 by 3 pi a cube, and the surface area of a sphere is 4 pi r square, or so r is a. So we should be getting these answers. All right. If you get an objective question, you directly have to give these answers. However, to see how this method works for us, to get a feel of this, we will have to use this. So now let us start. Let us draw the curve. Let us draw the circle first. This is the origin, radius is a. Now, a very important point is that we are revolving about the x-axis like this. So it keeps revolving about the x-axis and the circle, and a solid is generated. Now we want to find now we want to find the volume and the surface area. To find the volume, one thing we should know that this is not a function. This curve is not a function because a vertical line cuts the curve in 2 points. So for the same value of the abscissa, there are 2 values of the ordinate. However, this curve can be written as y is equal to plus root of a square minus x square, and the lower portion below the x-axis will be y is equal to minus root of a square minus x square. Okay. Now, to find the volume, we have to integrate from, this is minus a to a. Integrate this strip okay. Yeah. So this strip This is the volume. This is dx at a distance of x. This value will be y here. So volume of solid of revolution. About the x-axis is v is here in this case. What is this strip? This is y, right? So pi y square dx integral from x equal to minus a to a. So this is easy. So minus a to a pi y square is a square minus x square times dx. Okay. So now this is an even function. So you can write twice of integral 0 to a pi a square minus x square dx. So this will be 2 pi times, when we integrate, you will get a square x minus x cube by 3. A square x plus minus x cube by 3 from 0 to a. This is 2 pi. Substitute the upper limit a cube minus a cube by 3 minus 0 by 3. Substituting the upper limit and the lower limit. So we get 2 pi times 3 minus 1 is 2a cube upon 3. So you get 4 upon 3 pi a cube, which was our expected answer. 4 by 3 pi a cube. This is our expected answer. This volume. Okay. Next, we have to find the surface area. Surface area of the solid of revolution. About x-axis is S is equal to, what do we get? 2 pi y, but because we are talking about surface area, it's a curved surface area, ds we have to take. For volume, we take dx, but for surface area, we have to take ds. So 2 pi y ds, 2 pi y ds integrated. Now we have to integrate with respect to x. So 2 pi under root a square minus x square, and ds is under root of 1 plus dy by dx the whole square dx. So y is under root of a square minus x square. Dy by dx will be 1 over 2 root a square minus x square multiplied by the derivative of a square minus x square by chain rule. So we get minus x by under root a square plus minus x by under root a square minus x square. So this is what we get for dy by dx. So now if we substitute this, what we are going to get is integral. Now limits minus a to a. 2 pi taken common, minus a to a, under root of a square minus x square, 1 plus x square by a square minus x square dx. So 2 pi integral minus a to a under root of a square minus x square. Now this is numerator root of a square minus x square plus x square by under root of a square minus x square dx. So this term and this term are there both in numerator and denominator. They get cancelled. And this minus x square and x square also get cancelled. So we are left with 2 pi integral minus a to a root a dx, root of a square dx, which is a. So this is 2 pi a, that's x from minus a to a integral. So this is 2 pi a into a minus of minus a, which is 2a. So 2 pi a square into 2a, 4, oh, not a square, it is, this is a. 2 pi a into 2a is 4 pi a square. 4 pi a square. That's what was our expected result. Yes, 4 pi a square. So that's the way to do a volume of revolution of a plane curve, volume of solid of revolution, and volume of the surface area of the solid of revolution. Okay, next. Is it clear? Have you taken down? I'll go to the next problem. Let's do the second problem. The part of the parabola y square is equal to 4ax cut off by the latus rectum revolves about the tangent at the vertex. Find the volume of the solid of revolution. Surface area is a much involved problem in this. It will be a very lengthy one, but we can still try, those who want to try. However, let's do this. Now we have this parabola. Y square is equal to 4ax is a parabola It's a standard parabola that we know. Okay. Now, latus rectum is a chord that passes through the focus and perpendicular to the axis of the parabola. So this is the latus rectum. The endpoints of the latus rectum we know are a comma 2a and a comma minus 2a. Okay. So now how do we find now what is the tangent at the vertex? Vertex is the origin. Tangent at the vertex is the x-axis. So which portion of the parabola we need to consider? So this portion. So this portion of the parabola is revolved about the tangent at the vertex. So when we do that, we'll get a curve like this. Okay, we get a curve like this. Now we want to find the volume thus generated. Now, which is easier, integrating with respect to x or integrating with respect to y? Both. When we do integration with respect to x, the solid of revolution will be this part, not this part. We'll have to integrate with respect to y, and from minus 2a to plus 2a. Okay. So let us see the differential element that we take. This will be the differential element. So what will be the integral volume of the solid of revolution? This volume is equal to pi x square dy integrated from y is equal to minus 2a to 2a. Now, what is x? Is y square by 4a. So easy. So this is integral minus 2a to 2a y. Y square is equal to 4ax, which means x is equal to y square by 4a. Okay. So x square will be y square by 4a the whole square times dy. Now this is an even function, so we'll get twice of integral 0 to 2a, twice of integral 0 to 2a, and pi taken outside, we'll get y power 4 upon 16a square dy. Y power 4 upon 16a square dy. So this will be 2 pi by 16a square into integral of y power 4 is y power 5 upon 5 0 to 2a. So 2 pi by 16a square, then 2a to the power 5 upon 5. 2 power 5 is 32. 2 power 4 is 16. So we get 2 pi into 32 a power 5 by 16 a square times 5. So this simplifies to 16 to 32. So we get 4 pi a cube upon 5. 4 pi a cube upon 5 cubic units. This will be the volume of the solid of revolution. Okay, clear?
Yes, sir.
All right. Now I'll give you another problem. Please solve right now. Find the volume of the solid of revolution generated by revolving x square by a square plus y square by b square equal to 1, a greater than b, about the major axis, the minor axis, about the major axis and the minor axis. Okay, I'll give you time. Shall I give you 3 minutes? Let us see. Can you make it in 3 minutes? Please start. You can just do the first one. The second part you can do that later. First part about the major axis we can do. One answer. Doesn't seem to be right. Good. And one answer I've got correct. Correct answer. Let's see others. Okay. So I'll stop. So I've given you 4 minutes time to solve this problem. So now let us look at the solution. This is an ellipse. There's the x-axis and the y-axis. Now, let us say this is the major axis. X-axis is the, actually, if these are the points AB form the major axis. CD forms the minor axis. So x-axis is, or the major axis is along the x-axis. Now, about this, if we have to revolve, you will form an ellipsoid. This volume is called as an ellipsoid. How to find? So simple, the volume. Volume is given by pi y square dx integrated from what is the ends of the ellipse, minus a comma 0 to a comma 0. Okay. Now, what is y square? From the equation of the ellipse, x square by a square plus y square by b square equal to 1. Ellipse y square will be 1 minus x square by a square times b square. This is what it will be. So integral pi b square times 1 minus x square by a square. Equal to minus a to a. When you integrate this, pi b square, and because it's an even function, this is an even function, this will become twice of integral 0 to a 1 minus x square upon a square dx. So when we do this, pi b square times 2, when you integrate, we get x minus x cube by 3a square from 0 to a. So 2 pi b square times a minus a cube by 3a square. You will get a by 3 minus of 0 minus 0. This is 2a by 3. 2 pi b square into 2a by 3 is 4 pi a b square by 3. So 4 by 3 pi a square a b square. And if a was equal to b, then it forms a circle. Then it will become 4 by 3 pi a cube. So that is the sphere. So this is the answer, 4 by 3 pi a b square. Similarly, for minor axis, this is about the major axis. About the minor axis, you can solve it yourself. About the minor axis, the volume of the solid of revolution is 4 by 3 pi a square b. We'll have to integrate with respect to y, and we'll be able to do it. So please check this. Okay. Next, so we did a simple Cartesian. We used Cartesian coordinates for integration so far in all the problems. Now let us use parametric equation. Let us do this. Question number 4. Question 4. Find the volume and surface area of the solid generated by the revolution of the curve x is equal to a cos cube theta, y is equal to a sine cube theta about the x-axis. This curve, do you remember what this curve is? X lies between minus a and a, y lies between minus a and a. Okay, parametric curve. If actually we remove this and see, this curve in Cartesian form is this: x by a to the power 2 by 3 plus y by a to the power 2 by 3 is equal to 1. Cos square theta plus sine square theta equal to 1. This gives x to the power 2 by 3 plus y to the power 2 by 3 is a raised to the power 2 by 3. So this what we remember what this curve is. This is an asteroid. Now, even let's say it is difficult to remember this curve, just rough. I'm drawing accurate, but you can draw roughly. Some basic aspects of the curve should be right. One thing is that x and y both lie between minus a and a. X lies between minus a and a. Y lies between minus a and a. And we have shown this, that it is symmetric about x-axis, symmetric about y-axis, symmetric about both axes, symmetric about origin because of x square, y square. And we drew this curve asteroid. So even if you're not able to accurately draw the curve. We just need to have some approximation. If we identify x coordinate, y coordinate, okay. Now I want, this is revolved about the x-axis. So it is like a solid with a 3D star shape kind of a thing. It's a now, and we want to find the surface area. Very difficult to do it by Cartesian coordinates, but anyway, let us do now. This is the strip dx at a distance x. This is y. So volume of the solid of revolution. Volume of the solid of revolution, V, is pi y square dx between x ranging between -a to a. Now, this will be a very difficult integral if we resort to, of course, we can do root of a to the power 2 by 3 minus x to the power 2 by 3 and substitution and all. Directly we have x is equal to a cos cube theta, y is equal to a sin cube theta. So d, this is minus a to a pi y square dx will be written as dx upon d theta times d theta. So now we have to convert to theta. We were integrating with respect to x. Now we have to convert to theta. Now x is equal to a cos cube theta. When x is equal to a, when x is equal to a, cos cube theta will be 1. So theta will be 0. And when x is equal to minus a, cos cube theta will be -1. That means theta is equal to pi. So from 0 to pi. So now let us change this. It will be integral. At minus a, it is pi. At a, it is 0. Sorry. Yeah, 0. And then pi y is a sine cube. So a sine cube theta times dx by d theta. Dx by d theta is 3a cos square theta times minus sine theta d theta. Okay. So now this reverse the limits of integral, removing this minus sign, we get 3 pi a square. A 3 pi comes out 0 to pi sine to the power 4 theta into cos square theta. Now this is not in Wallis formula, because Wallis formula is valid for integral from 0 to pi by 2. It is not for pi. But we have this rule, integral 0 to 2a f of x dx will be twice of integral 0 to a f of x dx if f of 2a minus x is equal to f of x. So this is one property in definite integrals. So sine of pi minus theta is sine theta. So that will not change. So sine power pi minus theta will be sine theta itself. Cos of pi minus theta is minus cos theta. However, because of the square, again it remains cos theta. So this, for this particular case, we get f of pi minus theta is equal to f of theta. So pi is taken as 2a. So this will be same as twice of integral 0 to pi by 2 sine power 4 theta cos square theta d theta. This is, what is this? 2a is taken as pi. That means a is pi by 2. So 2 times pi by 2 minus theta is f of 2 pi by 2 minus theta is equal to f of theta. So it is 0 to pi by 2. So we get 6 pi a square into, apply the Wallis formula now for this integral, 3 into 1 upon 4 plus 2, 6 into 4 into 2, and both are even powers, so multiply by pi by 2. So 6 and 6 cancels. So oh, I'm sorry, I made a big mistake. This is y square. This is y square pi y square dx. So this will become sine to the power 7 theta. 6 plus 1, 7 theta. Okay. Other things remain as it is. This becomes a cube. This becomes a cube. 3 pi a cube. Sine power 7 theta cos square theta. So this is 3 pi a cube. This remains same, 2 power. This thing changes. 2 times. This is Wallis formula now will be 6 into 4 into 2, and this is 1 divided by 7 plus 2, 9, 7, 5, 3, 1. Pi by 2 doesn't come because one of them is odd. Both of them should be even for pi by 2. So let us see what cancels. Six, 36. So 9 will definitely cancel. 9 4s 36. And then now all are even factors in the numerator, and denominator are odd factors. So you cannot change now. Now 4 4 16, 16 to 32 to 64. Oh, this is 3 into 2. This remains 3. I'm sorry. This is 3. So 6. So this is 2. 9 strikes. 6 3 is 18, 2 times. So we have 2 into 2, 4, 16, 32. So 32 pi a square upon 7 pi is 35 times 3, 105. So this was the volume of the solid of revolution. Okay, now let's do the surface area. So surface area of the solid of revolution. Now for the surface area, we will take, instead of dx, we'll have to take ds here. So 2 pi y will be the circumference. This is y. So when we revolve it, the surface that is generated will have a circular surface, circular disk, will have y as the radius. So 2 pi y times ds. So surface area of the solid of revolution is 2 pi y ds integral. Now we will have to convert it. We are revolving about the x-axis. So it will be the same limits x and theta. When x is equal to a, theta is 0. When x is equal to minus a, theta is pi. So now this one will be 2 pi y into dx by d theta whole square plus dy by d theta whole square under root times theta. Theta varies from, now we wanted to do with respect to x, now it will be with respect to theta. So minus a to a will be pi to 0. Now let's do this. So x is equal to a cos cube theta, y is equal to a sine cube theta. Now dx by d theta is equal to 3a cos square theta into minus sine theta. Dy by d theta is 3a sine square theta times cos theta. So substituting this, we'll get 0 to pi. 2 pi y is a sine cube theta. Okay, a sine cube theta, and under root of this square, this we'll get 9a square cos power 4 theta sine square theta plus 9a square sine power 4 theta cos square theta d theta. We can write this as integral 0 to pi. Omit the negative sign because surface area, you can omit the sign. Now this is 9a square comes out and becomes 3a, and that a multiplies with this a gives 3a square sine cube theta under root of sine square cos square theta sine square theta times cos square theta plus sine square theta d theta. So this is 6 pi a square integral. Now sine of pi minus theta will be sine theta, cos of pi minus theta will be minus cos theta. So you can write this as 2 times 0 to pi by 2 sine cube theta. And now you can remove the under root. You will get sine theta cos theta. So we get 12 pi a square integral 0 to pi by 2 sine power 4 theta cos theta. Of course, you can do Wallis formula, or you can write sine theta as t, cos theta d theta will be dt. Like that you can also do by substitution. By Wallis formula, this is 3 into 1 into 1 by 4 plus 1, 5 into 3 into 1. So you get 1 by 5. So 12 pi a square upon 5 square units. All right. I will stop now, but I will give you 2 problems for solving. You can take down these problems. Question. This was question 4. I'll give you question 5. Find the volume generated by revolution of one arc of the cycloid x is equal to a into theta minus sine theta, y is equal to a into 1 minus cos theta about its base. Volume and also find surface area. I'll give answers. You can verify your solution. Volume is 5 pi square a cube. Surface area 64 pi a square by 3. Take this down. Try to solve it. And one, so on cardioid, attempt this. Tomorrow's class we'll discuss, and then we proceed further. Find the volume and the surface area of revolution of the curve r is equal to a into 1 minus cos theta. What is this? It's the cardioid about the initial line. Okay, answers. Volume is 8 pi a cube by 3. Surface area 32 pi a square upon 5. Okay, attempt these 2. All right, have you taken down, everyone?
Yes, sir.